Hello, today I will be talking about Lab 5, Choose Your Own Adventure, Motion of a Slinky. Introduction. First, we need to analyze the motion of a slinky by first creating a plot from the experimental position versus time data obtained in Tracker, and two, creating two VPython models, one without drag and one with drag force. The one without drag will only account for the gravitational force, and the one with drag force will account for both gravitational force and drag force. After doing this and creating a Google spreadsheet file with all the data from the three models, the conclusion I obtained is that the motion of the spring is more accurately predicted by the model that adds drag force than the model that does not obtain it. Also, I observed that the bottom of the slinky does remain motionless, and that this effect is caused by opposing forces acting on the multi-particle system of the slinky at all times. This effect is better explained when the motion is analyzed as a multi-particle system, but in order to be able to model the motion on Python, I treated the slinky as a point particle system. Fundamental principles: when modeling the slinky as a point particle system, the only forces acting on it are the gravitational force and the drag force. The gravitational force is determined by Newton's second law of gravitation, which is V final equals V initial plus F net over mass times delta t. The F net is determined by the force of drag plus the force of gravitation. Other important equation we need to take into consideration is the equation for drag force, which is responsible for the motion observed in our second model. This equation is Fd equals b times mag ball velocity squared, where b is the proportionality constant and Fd equals drag force. For the tracker model, I set the origin on the hand with the x position on the horizontal axis and the y position on the vertical axis. Also, you can see my position versus time data obtained right here on the left. For the VPython model 1, which only accounts for the gravitational force, we have these initial conditions. The slinky position is 0 in the x vector, negative 0.596 in the y, and 0 in c. Slinky velocity is 0 meters per second. The other initializations we have is that delta t equals 0.033 seconds, gravity equals 9.8 meters per second squared, j hat, which is only the unit vector used for modeling the gravitational and drag forces. Also, in this model, you can see right here that I put the b equals 0, which is a proportionality constant for drag force. For the calculation loop, I set it for time less than 0.52 seconds, which equals weight equals the negative mass of the slinky times gravity times j hat, and F net equals weight. Then the velocity is predicted by Newton's second law, which is the velocity of the slinky equals velocity final of the slinky equals velocity initial plus F net over mass times delta t. And the position is obtained by the derivation of the Newton's second law, which is position final equals position initial plus velocity of the slinky times delta t. Also, you can see here that I put print to print time and slinky position. What I obtained from this is that, as you can see, the yellow arrow in the blue ball represents the gravitational force. This is the graph model I obtained, and in the top you can see time and the vector, and this vector is the position obtained when only modeling the gravitational force. In the VPython model 2, we know that the slinky position, the initial conditions are the same as in the VPython model 1, and the only difference in the other initialization is that we have a proportionality constant. And for the calculation loop, we added drag force. When we run this code, we obtain that the final y position equals negative 1.649, which is very close from the negative 1.648 final position we obtained from Tracker. Comparing VPython models. The blue line equals the experimental position, the red line is the VPython model 1, which only accounts for gravity, and the yellow line accounts for drag force. As you can see, the model that best predicts the experimental position is the Python model 2, which is the one that models drag force. It is important to note that the difference between the Python model 2 and the experimental position might happen because of human error when calculating the center of mass of the spring. So why does the bottom of the slinky remain motionless? What is actually happening is that when the slinky is let slack, it is in equilibrium between the force of gravity pulling down and the force of the spring pulling up. The length that the slinky will slack is the exact same length that causes the entire spring to have gravity of tension, which is this one. Then, when you let the top of the spring go, it experiences a force of G plus G, the top of it. Then the bottom of the spring experiences a force of G plus negative G. So, and it just sits there, like it's shown in the picture to the right. When the spring collapses completely, it is momentarily not accelerating, as all the spring forces cancel out, which is in this case, and then gravity takes over, and it falls as a whole system. Thank you for watching.